Close your eyes and travel back with me. Back through time itself. Back to when your Earth was nothing like the world you know today. 4.5 billion years ago, there were no earthquakes. There were no mountains piercing the sky. No valleys carved by ancient rivers. No continents drifting slowly across vast oceans. Your planet was young then. So very young. Picture a ball of molten rock floating in the darkness of space. This was Earth in its infancy. A glowing ember among the stars. The entire planet was liquid fire, hotter than any furnace you can imagine. Every grain of what would become soil, every pebble that would rest on future beaches, every crystal that would sparkle in mountain caves, all of it flowed like honey made of stone. There was no solid ground to stand on. No place for water to pool. The young Earth spun through space like a drop of melted metal, beautiful and terrible and completely alone. But even in that blazing heat, something magical was beginning to happen. Your planet was learning how to cool down. Space is cold. Colder than the deepest winter night. And heat always flows from warm places to cold places, like water flowing downhill. So Earth's fiery surface began to lose its heat to the endless black around it. Slowly. So slowly that millions of years passed like single breaths. Think of hot soup cooling in a bowl. At first, steam rises from the surface. The soup stays liquid, too hot to touch. But as heat escapes into the air, something changes. A thin skin begins to form on top. This skin wrinkles when you blow on it. It's fragile. If you stir the soup, the skin breaks apart and disappears back into the liquid below. This is exactly what happened to your Earth. As the planet's surface cooled, the first thin skin of solid rock began to form. Scientists call this the first crust. But it wasn't like the thick, stable ground beneath your feet today. It was delicate. Fragile as ice on a spring pond. The molten rock beneath this new crust was still churning. Still moving. Still incredibly hot. Sometimes the liquid rock would push upward, breaking through the thin skin like bubbles rising in thick pudding. The solid crust would crack. Melt. Disappear back into the fiery ocean below. Then the cooling would begin again. A new skin would form. Thicker this time. Stronger. For millions of years, this dance continued. Cooling and heating. Solidifying and melting. Your Earth was learning how to have a solid surface. Learning through trial and error, the way a child learns to walk by falling down and getting up again. During this time, Earth was utterly silent. No wind could blow because there was no atmosphere thick enough to carry sound. No waves could crash because there were no oceans yet. No life stirred because nothing could survive in this world of liquid stone. But the silence was not empty. It was full of potential. Full of the quiet work of creation happening grain by grain. Molecule by molecule. As more time passed, tens of millions of years, hundreds of millions of years, the crust grew thicker. More stable. The cooling skin of rock became strong enough to last for thousands of years without melting. Then millions of years. Your Earth was developing its first permanent solid surface. Imagine the moment when the first patch of rock stayed solid for an entire million years. That small area of crust became Earth's first tiny continent. No bigger than a city, perhaps. But it was solid. It was permanent. It was the beginning of all the land you know today. This first stable crust was dark. Darker than any rock you've ever seen. It was made mostly of a rock called basalt, the same kind of rock that forms when underwater volcanoes cool today. Basalt is heavy and dense, like a stone that has been squeezed tight by powerful hands. But even as this first crust formed, something else was stirring deep below. The molten rock beneath the surface wasn't just sitting still. It was moving. Flowing in great, slow currents like an ocean made of liquid stone. These currents carried heat from Earth's center toward the surface. They moved in giant circles, rising in some places and sinking in others. These flowing currents would become the engine that powers everything you're about to discover. They would create the first cracks in the young, smooth crust. They would teach the continents how to move. They would give birth to Earth's first earthquake. But in these early days, the planet rested in that profound silence. The crust was still learning how to be solid. The liquid rock below was still learning how to flow in patterns. Everything was preparing for something magnificent to begin. As you drift toward sleep tonight, picture that young Earth cooling in the darkness. See the first patches of solid ground forming like islands in an ocean of molten stone. Feel the deep quiet of a world getting ready to dance. Soon, that perfect stillness would be broken by the first stirrings of something that continues even now, as you rest. Deep beneath your sleeping body, the same forces that shaped that ancient world are still at work, still moving, still preparing the next chapter in Earth's long, slow dance. Now your Earth has begun its most delicate work. The work of growing skin. Picture yourself on a winter morning, watching frost form on a window. At first, there's nothing. Just clear glass and cold air. Then, so slowly you can barely see it happening, tiny crystals begin to appear. They spread across the surface like silver lace. Each crystal finds its perfect place. Each one connects to the next in patterns more beautiful than any human artist could design. This is how Earth's first solid crust began to form. Not all at once, but crystal by crystal. Mineral by mineral. Each tiny piece finding its place in the growing puzzle of solid ground. As the molten rock at Earth's surface cooled, something magical happened inside it. The atoms, those impossibly small building blocks that make up everything, began to slow down. When rock is liquid and hot, its atoms dance wildly, bouncing off each other like children at play. But as the temperature dropped, the atoms began to move more slowly. More carefully. They started to arrange themselves in orderly patterns. Like dancers learning choreography, they found their positions and held them. This is how the first minerals were born. Imagine each mineral as a different kind of crystal puzzle. Some minerals, like quartz, arrange their atoms in neat, geometric shapes that sparkle when light hits them just right. Others, like feldspar, create crystals that look like tiny rectangular buildings. Each mineral has its own special pattern. Its own way of organizing the dancing atoms into solid, stable structures. As Earth's surface cooled, these different minerals began to form at different temperatures. It was like watching a garden grow in reverse time. First, the minerals that needed the most heat crystallized from the cooling rock. Then, as the temperature continued to drop, minerals that preferred cooler conditions began to appear. The very first crust was made mostly of dark, heavy minerals. They created rocks that were black as a moonless night. This early crust was thin, thinner than the shell of a bird's egg. If you could have walked on it, you would have felt the tremendous heat still radiating from below. The solid ground would have been warm beneath your feet, like stones that had been sitting in summer sunshine all day. But this fragile skin was stronger than it looked. Day by day, year by year, it grew thicker. More stable. The minerals locked together like puzzle pieces, creating a surface that could support its own weight without melting back into the fiery ocean below. As millions of years passed, something wonderful began to happen. The growing crust started to trap heat inside the planet. Like a blanket over sleeping Earth, the solid rock layer helped keep the interior molten and active. This was important. Very important. Because that liquid rock below would soon become the engine that moves continents and creates earthquakes. During this time, your Earth was learning to breathe. Heat from the planet's core needed to escape somehow. It couldn't stay trapped forever. So it found ways to rise through the solid crust. Sometimes the heat would create weak spots where the rock would crack and allow molten material to seep through. Sometimes it would push up from below, creating the first tiny bumps and hills on Earth's otherwise smooth surface. These were Earth's first breaths. Slow, deep movements as the planet learned to release its inner energy without destroying the precious solid skin it had worked so hard to create. The early crust was not uniform. Not smooth like a marble. In some places, it grew thick and strong. In other places, it remained thin and fragile. These differences weren't random. They followed patterns created by the currents of molten rock flowing beneath the surface. Where hot currents rose from deep inside the Earth, the crust stayed thin. The rising heat would partially melt the solid rock from below, keeping it soft and pliable. Where cooler currents sank back toward the planet's center, the crust grew thick and stable. This created Earth's first geography. Not mountains and valleys as we know them today, but gentle rises and shallow dips in the otherwise flat surface. The beginnings of landscape. The first hints that Earth would not remain a perfectly smooth sphere forever. As the crust continued to thicken, it began to develop what scientists call differentiation. This means that different kinds of rocks began to form in different places. It's like baking a cake where some parts end up lighter and fluffier while others become dense and heavy. The lighter rocks tended to rise toward the surface. They were made of minerals like quartz and feldspar, materials that would eventually become the foundation of continents. The heavier rocks, rich in iron and magnesium, settled lower. They would become the foundation of ocean floors. But all of this was happening so slowly. So incredibly slowly. If you could have watched from space, Earth would have seemed perfectly still. Years would pass with no visible change. Decades. Centuries. The planet appeared frozen in time. Yet beneath that appearance of stillness, profound changes were taking place. The crust was organizing itself. Preparing itself. Growing stronger and more complex with each passing million years. Think of a potter working with clay. At first, the clay is just a shapeless lump on the wheel. But as the potter's hands guide it, the clay begins to take form. Walls rise. The shape emerges slowly, patiently, through countless small adjustments. Earth was its own potter during this time. The forces of heat and cooling, pressure and release, were shaping the planet with infinite patience. Creating a surface that would be strong enough to support the great dance of moving continents that was soon to begin. As you rest tonight, feel the solid ground beneath you. Know that this stable surface that holds you safely is made of billions of crystals, each one formed during those quiet early years when Earth was learning to be solid. Each mineral grain in the rock below your home once crystallized from molten stone, finding its place in the growing skin of a young planet. The crust is complete now. Strong and thick and ready. But deep below, something is stirring. The same heat that created this solid surface is beginning to move in new patterns. Patterns that will soon teach the continents how to dance. Beneath the solid skin you've watched form, something magnificent is stirring. Something that will change everything. Deep inside your Earth, below the growing crust, lies a layer of rock unlike anything you can touch or see. Scientists call it the mantle. It makes up most of your planet's interior. A thick shell of rock wrapped around Earth's glowing heart. But this rock is not like the stones in your garden. It's not like the solid granite of mountains or the hard marble of statues. The mantle rock is hot. So incredibly hot that it behaves like thick honey. Like molten glass cooling in a furnace. It's solid, yes, but it flows. Slowly. Patiently. Powerfully. Imagine holding a piece of warm taffy in your hands. At first, it seems solid. But as you pull gently, it stretches. It moves. It flows like liquid, but slower. Much slower. This is how the mantle behaves, except the taffy is made of rock, and the pulling happens over millions of years. The heat that makes this possible comes from Earth's very center. The core. Picture a ball of iron and nickel as hot as the surface of the sun, spinning at the heart of your planet. This core has been burning with leftover heat from Earth's violent birth, when countless space rocks crashed together to form your world. It also creates new heat through the slow decay of radioactive elements trapped inside the planet when it formed. This heat must go somewhere. It cannot stay trapped forever in the core. So it begins a long, slow journey upward. A journey that takes millions of years to complete. The heat travels through the mantle in currents. Think of a pot of thick soup warming on a stove. The soup at the bottom gets hot first. As it heats up, it becomes lighter and begins to rise. The cooler soup at the top sinks down to take its place. Soon, the entire pot is moving in slow, circular patterns. The soup rolls and flows in invisible rivers of warmth. This is exactly what happens in Earth's mantle. Hot rock rises from deep below. Cool rock sinks from higher up. Giant currents of flowing stone carry heat from the core toward the surface in patterns as regular as breathing, as steady as a heartbeat. These currents are enormous. Imagine rivers of flowing rock thousands of miles wide. Streams of hot, moving stone that stretch from the core almost all the way to the surface. They move so slowly that it would take a piece of rock 30 million years to complete one full trip from bottom to top and back again. But slow doesn't mean weak. These currents are incredibly powerful. They carry enough energy to move entire continents, to crack the strongest rocks, to reshape the surface of your planet grain by grain, year by year, age by age. As the hot rock rises, it pushes against the solid crust above. Like a giant, invisible hand pressing upward from below. The pressure builds slowly, steadily. The crust begins to bulge upward in some places. In other places, where the currents sink back down, the crust gets pulled and stretched. This is where the story of earthquakes truly begins. Not with the shaking ground you might imagine, but with this slow, persistent pushing and pulling from deep below. The mantle currents are setting the stage for everything that will follow. The rising currents don't push up randomly. They follow patterns. Scientists have discovered that hot rock tends to rise in long, narrow columns called plumes. Picture smoke rising from a campfire, but imagine that smoke is made of rock so hot it glows, and it rises through solid stone instead of air. These plumes of rising rock create weak spots in the crust above them. Places where the solid surface becomes thin, fragile, ready to crack under pressure. The plumes carry not just heat, but also the force that will eventually split continents apart and push them across the globe. Where the currents flow sideways, just below the crust, they drag the solid rock above along with them. Imagine honey flowing beneath a thin sheet of ice. The flowing honey would pull and tug at the ice, creating cracks and causing pieces to move. This is what the mantle currents do to Earth's crust. But remember, all of this happens in what scientists call deep time. Time so slow that mountains can rise and disappear while the currents complete just one cycle. Time so patient that entire species of animals can evolve and go extinct while a piece of mantle rock travels from one side of a current to the other. During Earth's youth, these currents were even more active than they are today. The planet was hotter then. The core burned more fiercely. The radioactive elements produced more heat. So the mantle churned faster. The currents flowed more vigorously. The pressure on the crust above was greater. This is why the first earthquakes were born during this time. The combination of a thin, fragile crust and powerful currents flowing beneath created perfect conditions for the solid surface to crack, to move, to dance. The currents also began to sort the materials in Earth's interior. Heavy elements sank toward the center. Lighter elements rose toward the surface. This process, called differentiation, helped create the different layers that make up your planet today. The dense iron core. The thick, flowing mantle. The light, solid crust. As this sorting happened, it released even more heat. More energy for the currents to carry upward. More force to push against the growing crust. The young Earth was like a vast engine, powered by its own formation, driving the movements that would shape its surface for billions of years to come. Even now, as you rest peacefully in your bed, these same currents are flowing beneath you. The same patterns that began when Earth was young continue today. The mantle still rises and falls in its ancient rhythm. Still carries heat from the core. Still pushes against the crust with patient, persistent force. But the currents are slower now. Gentler. The planet has cooled over the billions of years since its birth. The earthquakes are smaller. The movement's more subtle. Yet the dance continues. The restless heart below still beats with the pulse that will teach continents to move and oceans to spread. Feel that rhythm now, as sleep draws near. Deep below your dreaming body, rivers of rock flow in patterns older than life itself, carrying the heat that keeps your planet alive, setting the stage for the first great crack in paradise. Something extraordinary is about to happen on your young Earth. Something that will seem impossible until you understand the gentle secret beneath it all. The continents are going to learn how to float. Not float like a boat on water. Not float like a balloon in air. But float in a way that's far more beautiful and mysterious. They're going to float on rivers of rock. On currents of stone that flow like invisible streams beneath the solid ground. Picture a lily pad resting on the surface of a quiet pond. The lily pad seems to sit perfectly still, but if you watch carefully, you'll notice it moves. Slowly. Gently. Carried by currents flowing beneath the water's surface. The lily pad doesn't choose to move. It simply rides along with the flowing water below. This is how your continents move. They rest on top of the flowing mantle like lily pads on that peaceful pond. And just like the lily pad, they go wherever the currents beneath them carry them. But how can solid rock float on other solid rock? How can something as massive as a continent drift across the planet like a leaf on a stream? The answer lies in understanding that rock, like everything else in the universe, has weight. Some rocks are heavy. Some rocks are light. And when light things rest on top of heavy things, they float. The continents are made mostly of light rock. Rock filled with minerals like quartz and feldspar. These minerals are like the foam on top of a bubble bath. They contain lots of space between their atoms, which makes them surprisingly light for their size. Beneath the continents lies different rock. Heavier rock. Rock rich in iron and magnesium. This rock is dense and dark, like the deep water beneath the lily pad. It's strong enough to support the lighter continental rock above, but it's constantly moving. Constantly flowing in those ancient currents you learned about. As the heavy rock flows, it carries the light continental rock along with it. The continents become passengers on a journey they didn't choose, traveling on rivers of stone that flow slower than growing grass, but never stop moving. During Earth's youth, this floating system was just beginning to organize itself. The very first continents were small. Much smaller than the vast landmasses you know today. Picture them as islands of light rock scattered across a global ocean of heavier, darker stone. These early continents were like the first pieces of a jigsaw puzzle, but a puzzle that could rearrange itself. As the currents beneath them moved, the continental pieces began to drift. Some moved toward each other. Some moved apart. Some rotated slowly as they traveled, like leaves spinning in a gentle stream. The movement was so slow that if you could have stood on one of these early continents, you would never have felt it moving. Grass would grow at your feet faster than the ground beneath you traveled. Trees would sprout and live their entire lives without the continent moving more than a few inches. But time is patient. And over millions of years, inches become miles. Miles become thousands of miles. Continents that started next to each other slowly drifted to opposite sides of the globe. Others that began far apart gradually moved closer together. As they moved, something wonderful happened. The continents began to change the planet's surface in ways that had never happened before. When two continental pieces drifted toward each other, they would eventually meet. Imagine two lily pads floating toward each other on pond currents. When they touch, they don't bounce off. Instead, they push against each other. The edges might buckle upward. Wrinkles might form where they meet. This is what happened when early continents collided. The light rock couldn't sink down into the heavier rock below, so it had nowhere to go but up. The collision zones became Earth's first mountains. Not tall mountains like you see today, but gentle hills and ridges where the continental edges pushed against each other. When continents moved apart, something equally amazing occurred. As they separated, the heavy rock from below would rise up to fill the gap between them. This rising rock would cool and harden, creating new ocean floor. New pathways for the flowing currents beneath. The young Earth was learning to recycle itself. Old rock would sink back into the flowing mantle. New rock would rise to take its place. Nothing was permanent. Nothing stayed in the same place forever. The planet was becoming a living, breathing, constantly changing world. But the most important discovery was still to come. As the continents learned to float and drift, they also learned something else. They learned that they could break. The same forces that carried continents across the globe could also split them apart. When currents flowing in different directions pulled at the same piece of continental rock, cracks would begin to form. These cracks would grow deeper over time. Eventually, one continent would become two smaller pieces floating on their separate journeys. This breaking and drifting happened again and again throughout Earth's history. Continents would come together to form larger landmasses. Then they would break apart and scatter. Then drift back together again in different combinations. Like a slow-motion dance that has been going on for billions of years. The continents were also learning to grow. As they floated on the flowing rock beneath, they would sometimes pass over rising currents of hot mantle rock. These currents would add new material to the bottom of the continents, making them thicker, stronger, more permanent. Other times, continents would pass over sinking currents, and pieces of their edges would be pulled down into the flowing depths below. The continents would become smaller, more compact. The planet was constantly reshaping itself through this endless dance of floating stone. During this early time, the floating continents were changing the way heat moved through the planet. The light continental rock was like a blanket, trapping heat beneath it. This changed the flow patterns in the mantle below. New currents formed. Old currents shifted direction. The entire system of flowing rock adjusted to accommodate these floating islands above. As the continents drifted and the currents shifted, stress began to build in Earth's crust. The solid surface was being pulled and pushed in different directions at the same time. Like a sheet of ice on a pond when the water underneath starts to flow in opposing directions. Some parts of the crust were being stretched apart. Other parts were being squeezed together. Still other parts were being twisted as different sections moved at different speeds. The young planet's surface was accumulating tension, building pressure, preparing for something that had never happened before. The stage was being set for Earth's first earthquake. But that moment was still in the future. For now, the continents continued their gentle floating dance, drifting on currents of stone, learning the rhythm that would guide their movements for all of Earth's remaining history. As you settle into sleep tonight, know that the ground beneath you is still floating on those ancient currents, still riding the flowing rivers of rock that began their dance when Earth was young. The continents have never stopped moving. They never will. And somewhere in that slow, eternal dance, pressure is building once again, just as it did so long ago when Earth was preparing for its very first crack in paradise. For millions upon millions of years, your Earth has been building toward this moment. A moment that will change everything. The moment when paradise learns to crack. The young planet has been so patient, so gentle in its movements. The continents have been floating peacefully on their rivers of flowing rock. The currents beneath have been carrying them in slow, graceful patterns across the globe. Everything has been smooth, quiet, perfectly balanced. But beneath this peaceful surface, something has been growing. Something invisible but incredibly powerful. Stress. Pressure. The kind of tension that builds when forces push and pull in different directions at the same time. Imagine holding a thin stick between your hands. At first, you apply just a little pressure, bending it slightly. The stick curves but doesn't break. It's flexible. It can handle the gentle force. But as you slowly increase the pressure, the stick bends more and more. Until finally, there comes a moment when the stick simply cannot bend any further. That's when it snaps. This is exactly what has been happening to Earth's crust. The flowing currents beneath have been pulling the solid rock in different directions. Some areas have been stretched apart. Others have been squeezed together. Still others have been twisted as different sections of crust move at different speeds. For ages, the rock has been bending, flexing, accommodating these gentle but persistent forces. Rock is more flexible than you might think, especially when the pressure builds slowly over thousands of years. Stone can curve and bow like a branch in the wind, as long as the bending happens gradually enough. But there are limits to how much even the strongest rock can bend. Picture a vast sheet of stone stretching across hundreds of miles. This sheet has been slowly warping under pressure for centuries. In some places, it bulges upward like a gentle hill. In other places, it sags downward into shallow valleys. The rock is doing its best to accommodate the forces pulling and pushing it from below. But the forces are getting stronger. The currents beneath are flowing more vigorously as Earth's interior heat continues to drive them. The continents are moving faster. The pressure is building to a point that the crust has never experienced before. Somewhere on the young planet, at a place where multiple stresses have been building for thousands of years, the rock reaches its breaking point. It happens in an instant that has been millions of years in the making. The first crack appears as a thin line in the stone. Barely visible. Narrower than a hair. But it's the beginning of something momentous. Once that first tiny fracture forms, it creates a weak spot. A place where stress can concentrate and build even more rapidly. The crack begins to grow. It spreads through the rock like lightning frozen in slow motion. Not fast like the lightning you see in storms, but with the same jagged, unpredictable path. The fracture follows the weakest roots through the stone, zigzagging around hard minerals and following softer ones. As the crack grows longer, something remarkable happens. The rock on either side of the fracture begins to move. The immense pressure that has been building for so long finally has somewhere to go. The stone shifts, slides, adjusts its position to release the accumulated stress. This movement sends waves of energy rippling through the solid earth. Waves that travel faster than sound, racing through the rock in all directions from the breaking point. These are seismic waves, Earth's first earthquake signal spreading through the planet's body. The movement is subtle at first. If you could have been standing on the surface during this historic moment, you might not have felt anything at all. The first earthquake was gentle compared to the powerful tremors that would come later in Earth's history. But it was profound. It was the moment when your planet learned that solid ground could move. The crack that started so small continues to grow. As stress releases in one area, it builds up in others. The fracture extends deeper into the crust. Longer across the surface. More rock begins to shift and slide to accommodate the new reality of broken stone. Other cracks begin to form nearby. The original fracture has changed the stress patterns in the surrounding rock, creating new weak points. Soon, a network of cracks spreads through the crust like a spider web made of broken stone. But this breaking is not destruction. It's creation. Each crack that forms allows the rock to adjust to the forces acting upon it. The crust is learning to be flexible in a new way. Instead of bending until it breaks catastrophically, it's learning to break in small, manageable pieces that allow movement without complete collapse. This is how Earth discovered one of its most important abilities, the power to release pressure gradually through many small breaks rather than one catastrophic failure. The planet was learning to manage its own internal stresses through controlled cracking. As the first earthquake waves traveled through the young Earth, they carried information. The waves moved at different speeds through different types of rock. They reflected off boundaries between rock layers. They revealed the hidden structure of the planet's interior in ways that nothing else could. In a sense, Earth's first earthquake was also Earth's first song. The seismic waves created vibrations that rang through the planet like a bell struck for the first time. Different parts of the Earth resonated at different frequencies, creating a complex symphony of sound that only the rocks themselves could hear. The earthquake also marked the beginning of a new relationship between Earth's surface and its interior. Before the first crack, the crust had been a passive passenger, simply riding along on the flowing currents beneath. But now it had become an active participant in the planet's movements. The cracks provided pathways for communication between the surface and the depths below. Heat could escape more easily through fractures. Pressure could be released before it built to dangerous levels. The solid crust and the flowing mantle began to work together in new ways. As the first earthquake settled into stillness, something beautiful remained behind. The network of cracks created during that historic moment became the foundation for all the geological activity that would follow. These fractures would guide the formation of the first mountain ranges. They would determine where future continents would split apart. They would channel the flow of water and the movement of life across the planet's surface. The cracks also created Earth's first real geography. Before the earthquake, the planet's surface had been gently rolling but mostly uniform. Now there were distinct features. Places where the ground had shifted up. Places where it had dropped down. The first cliffs. The first valleys. The first hints of the dramatic landscapes that would eventually cover your world. But perhaps most importantly, the first earthquake taught Earth how to change. Up until this moment, the planet had been growing and cooling, but its basic structure had remained stable. The first crack introduced the concept of transformation. Of surfaces that could be completely rearranged. Of solid ground that could become something entirely different given enough time and pressure. The young Earth had discovered that being solid didn't mean being permanent. That stability could coexist with constant, gradual change. That the most beautiful and complex features of a planet come not from stillness, but from the careful balance between stability and movement. As you drift towards sleep tonight, remember that the ground beneath you still carries the memory of that first crack in paradise. Every earthquake that has ever shaken the Earth traces its lineage back to that first moment when solid rock learned it could break and move and transform while still remaining strong. The pattern was set then, in those first moments of breaking. But the dance was just beginning, and soon the cracks would learn to organize themselves into something even more remarkable, the boundaries where Earth's great plates meet and greet each other in their eternal, restless dance. Now that Earth has learned to crack, something beautiful begins to emerge from the broken pieces. The fragments of crust don't simply scatter randomly across the planet's surface. Instead, they organize themselves into something remarkable. Something that will define how your world works for the rest of its existence. These broken pieces become plates. Vast sections of Earth's outer shell, each one floating on the flowing rock beneath like enormous puzzle pieces on a sea of stone. But unlike the pieces of an ordinary puzzle, these plates are alive with movement. They drift. They rotate. They interact with each other in ways that create the most amazing geological theater you could ever imagine. The places where plates meet each other are where the real magic happens. These boundaries are like the edges of a dance floor where different partners come together to perform their ancient choreography. Each meeting place tells a different story. Each boundary dances to its own rhythm. Picture two people approaching each other across a room. They might embrace when they meet. They might pass by each other with a gentle touch. They might even collide and push against each other. The plates of Earth's crust interact in similar ways, but their dance is performed in slow motion over millions of years. Some plate boundaries are places of greeting and embrace. Here, two plates move toward each other like old friends meeting after a long separation. But when plates embrace, something extraordinary happens. One plate slides beneath the other in a gesture of graceful submission. Imagine a dancer taking a deep, elegant bow. As she bends forward, her body curves downward in a smooth, flowing motion. This is exactly what happens when one plate meets another and decides to dive deep into the Earth. Scientists call this subduction, but you can think of it as the planet's most patient bow. The diving plate doesn't disappear. Instead, it travels on a long journey back into the hot interior of the Earth. As it descends, it carries pieces of the surface world with it. Sediments from ancient ocean floors. Minerals that once sparkled in sunlight. Even traces of early life, if any existed at the time. This descending plate becomes a messenger, carrying news from the surface down to the deep, flowing currents of the mantle. And the mantle responds by sending its own messages back up. Hot rock rises to fill the space left behind, creating new crust, new land, new opportunities for the surface world to grow and change. Other plate boundaries are places of separation and farewell. Here, two plates move away from each other like dancers stepping apart at the end of a song. As they separate, something wonderful happens in the space between them. New rock rises from below to fill the gap. Picture two pieces of ice floating apart on a pond. As they drift away from each other, the water beneath becomes visible in the growing space between them. At plate boundaries where separation occurs, hot rock from the mantle rises up like that water, cooling and hardening to become new ocean floor. These spreading boundaries are nurseries where new crust is born. The rock that emerges is young and fresh, still warm from its journey up from the depths. It carries heat and minerals from deep inside the earth, creating underwater mountain ranges and valleys that stretch for thousands of miles. The process is gentle but persistent. New rock emerges at these boundaries at about the same rate that your fingernails grow. Inch by inch, year by year, the ocean floors spread wider. The plates drift apart. The Earth slowly expands its surface area as new crust is created. But perhaps the most dramatic plate boundaries are the places where plates slide past each other like dancers changing partners in an elaborate routine. Here, the plates neither embrace nor separate. Instead, they grind against each other in a slow, powerful friction that can last for millions of years. Imagine two massive stone wheels rolling in opposite directions, their edges touching. The contact point between them experiences enormous pressure. The rock heats up from friction. Sometimes it melts. Sometimes it fractures into countless small pieces. Sometimes it transforms into entirely new types of stone under the intense stress. These sliding boundaries are places of tremendous energy. The friction between the moving plates builds up over long periods of time, creating stress that eventually must be released. When the release comes, it often happens suddenly, causing earthquakes that can be felt for hundreds of miles. But even these violent releases are part of Earth's natural way of managing the enormous forces created by plate movement. The planet has learned to release pressure in many small events rather than allowing it to build to catastrophic levels. It's a form of geological self-regulation that keeps the system stable even as it remains constantly active. At some boundaries, the story becomes even more complex. Instead of just two plates meeting, three or more plates come together at what scientists call triple junctions. These are the geological equivalent of a complicated dance involving multiple partners, each moving in their own direction while trying to coordinate with the others. Triple junctions are places of incredible creativity. The competing movements of three different plates can create unusual geological features. Twisted mountain ranges. Valleys that curve in unexpected directions. Volcanic chains that seem to follow no logical pattern until you understand the complex dance of plates beneath them. Each type of boundary creates its own characteristic features on Earth's surface. The embracing boundaries, where one plate dives beneath another, often create chains of volcanoes. The descending plate releases water and other materials as it heats up, and these materials rise to create magma that eventually reaches the surface. The separating boundaries often create underwater mountain ranges called mid-ocean ridges. These ridges are like underwater spines running through the ocean basins, constantly growing as new rock emerges from below. Some of these ridges eventually rise above sea level to become islands or even continents. The sliding boundaries create long, straight valleys and mountain ranges. The friction between the plates grinds rock into fine particles and creates zones of crushed and altered stone that can extend for miles on either side of the boundary. As the plates continue their eternal dance, they reshape Earth's surface in ways both subtle and dramatic. Continents drift across the globe. Ocean basins open and close. Mountain ranges rise and erode away. Islands emerge from the sea and eventually disappear beneath the waves. But all of this happens so slowly that if you could watch it from space, most of the changes would be invisible. You would need to speed up time by millions of years to see the plates moving like the dance partners they truly are. The dance is not random. It follows the rhythm set by the flowing currents in the mantle beneath. As those deep currents change direction or speed, the plates above adjust their movements accordingly. The surface dance reflects the deeper dance happening in the planet's interior. Even today, as you rest in your bed, the plates beneath you are continuing their ancient dance. They move slower than the growth of your hair, but they never stop. Never rest. Never pause in their patient reshaping of the world. The boundaries where they meet and greet are still writing new chapters in Earth's long story, creating the mountains that will shelter future rivers and the valleys that will cradle tomorrow's lakes, in movement so gradual that they seem like stillness, yet so powerful they can lift stone peaks toward the stars. There is something deeply moving about watching a mountain being born. Not in the way you might imagine, with dramatic explosions and violent upheavals, but in the way it actually happens, with the infinite patience of stone learning to reach for the sky. Mountains are Earth's most beautiful sculptures, carved not by artists but by the slow collision of moving plates. They rise from dreams of stone, from the gentle but persistent embrace of continental masses that refuse to give up their dance. Picture two vast plates of Earth's crust drifting toward each other across the ocean of flowing rock beneath. They move slower than your hair grows, but they carry the weight of continents, the momentum of entire landmasses. When they finally meet, neither one wants to give way. Unlike the ocean plates that gracefully bow and dive beneath their neighbors, continental plates are too light to sink, too buoyant to disappear into the depths. When they collide, they have nowhere to go but up. The collision begins gently, so gently that for thousands of years, nothing seems to happen at all. The plates press against each other like two hands slowly coming together in prayer. The pressure builds. The rock begins to compress. But the changes are invisible to any eye that watches in human time. Deep beneath the point where the plates meet, the solid rock begins to behave like thick honey. Under enormous pressure and gentle heat, stone that has been rigid for millions of years starts to flow, to bend, to fold like fabric in the hands of a patient seamstress. Imagine taking a thick rug and pushing the ends toward each other. At first, the rug lies flat. But as you continue pushing, wrinkles begin to form in the middle. The wrinkles grow taller, more pronounced. Eventually, they become folds that rise high above the original surface of the rug. This is exactly what happens when continents collide. The flat layers of rock that once lay peacefully on the ocean floor begin to buckle and fold. Limestone that formed in shallow seas finds itself lifted thousands of feet into the air. Sandstone that was once a beach becomes the summit of a towering peak. The process is like watching origami performed by giants. Layers of rock fold over and under each other in patterns of incredible complexity. Some folds are gentle, creating rolling hills and broad valleys. Others are sharp and dramatic, forming knife-edge ridges that slice the sky. As the collision continues over millions of years, the folds grow higher. The pressure becomes more intense. Some layers of rock are pushed so hard they break and slide over their neighbors. These are called thrust faults, and they allow one section of mountain to climb on the back of another, creating peaks that tower even higher. The collision zone becomes a place of incredible creativity. The same forces that create the folds also generate heat. Rock that has never been hot since it first formed begins to warm up under the pressure. Some minerals transform into entirely new crystals. Some rocks partially melt and recrystallize into forms that sparkle with new beauty. Deep in the heart of the growing mountain range, pockets of molten rock form. This magma is different from the rock that rises from the mantle at spreading plate boundaries. It's created by the collision itself, born from the pressure and heat of continents embracing. Some of this magma rises to the surface, creating volcanoes along the spine of the growing mountains. But much of it cools slowly underground, forming large bodies of granite and other crystalline rocks. These granite cores become the strong backbone of the mountain range, supporting the folded layers above. As the mountains grow taller, they begin to affect the world around them in new ways. They create barriers to wind and weather. Clouds moving across the lowlands encounter these stone walls and are forced to rise. As they rise, they cool. As they cool, they release their moisture as rain and snow. The young mountains become centers of weather creation. They gather clouds around their peaks like crowns of white vapor. They channel winds through their valleys. They create their own climate, different from the flatlands around them. Water begins to carve the rising stone almost as soon as it appears above sea level. Rain falls on the high peaks and gathers into streams. The streams merge into rivers. The rivers cut valleys between the growing ridges, creating the complex topography that will define the mountain range for millions of years to come. This carving process is part of the mountain building dance. As the collision pushes rock upward, erosion wears it down. The two forces balance each other, determining how high the mountains can ultimately grow. Some ranges, where collision is rapid and erosion is slow, become incredibly tall. Others, where erosion keeps pace with uplift, remain relatively modest. But even as water and weather work to tear the mountains down, the collision continues to push them up. The dance between creation and destruction creates some of the most beautiful landscapes on Earth. Jagged peaks carved by ice and water. Gentle valleys filled with fertile soil eroded from the heights above. The mountains also become reservoirs of time. The rocks that form their layers contain the history of the Earth in their crystals and fossils. Limestone peaks hold the remains of ancient sea creatures. Sandstone cliffs preserve the patterns of long-vanished beaches. Shale slopes contain the compressed remains of prehistoric forests. As you trace the layers in a mountainside, you're reading the story of the planet's past. Each band of rock represents a different time in Earth's history. A different environment. A different chapter in the long story of life and stone. The collision that creates mountains doesn't happen quickly and then stop. It continues for tens of millions of years. Generation after generation of rock layers are folded and lifted. The mountain range grows not just taller, but also broader. More complex. More beautiful. Some collisions create mountain ranges that stretch for thousands of miles. Entire continents buckle and fold, creating vast highlands that reshape the planet's geography. These mountain-building events, called orogenies, are among the most powerful geological processes on Earth. Even after the collision ends, the mountains continue to change. They slowly rebound as erosion removes weight from their peaks. They adjust and settle as the forces that created them gradually relax. Some ranges continue to grow taller long after the plates that built them have moved on to new dances. The mountains become the planet's memory keepers. They hold the record of ancient collisions in their folded rocks. They preserve the story of how continents have come together and moved apart throughout Earth's long history. As you drift towards sleep tonight, imagine the mountains that surround your world. Each peak began as a dream of stone, born from the patient collision of ancient plates. Each ridge tells the story of Earth's slow but powerful embrace of its own moving pieces. And far beneath those towering peaks, in the depths of the ocean basins, another kind of creation is taking place, a different dance of rock and fire that builds the floors of the sea in patterns just as beautiful as the mountains that pierce the sky. Miles beneath the surface of Earth's oceans, where sunlight has never touched and silence reigns absolute, the most beautiful creation story on your planet unfolds every single day. It happens in darkness so complete that no eye has ever witnessed it directly. Yet it shapes the very foundation of your world with a rhythm as steady and reliable as your own heartbeat. Here, in the deepest places of the sea, Earth is constantly reborn. Imagine descending through the ocean's layers. Past the sunlit surface where waves dance and fish swim. Past the twilight zone where the last traces of daylight fade into blue-black mystery. Down into the abyss where the water is so deep it would crush any surface dweller, and the cold is so intense it would freeze any living thing that doesn't belong in these depths. At the very bottom of this dark world lies something extraordinary. A mountain range more vast and magnificent than any on land. These underwater mountains stretch for thousands of miles across the ocean floor, forming a continuous chain that wraps around the entire planet like the seam on a baseball. Scientists call these features mid-ocean ridges, but you can think of them as Earth's underwater spine. A backbone of stone running through every ocean basin, connecting all the seas in one grand, geological embrace. But these underwater mountains are unlike any mountains on land. They are not the result of collision and compression. Instead, they are places of separation and birth. Places where Earth literally pulls itself apart to create something new. At the crest of each ridge lies a crack. A valley that runs along the mountain's peak like a wound that never heals. But this crack is not a sign of damage. It's a doorway. A passage through which the planet's interior speaks to the world above. From this crack, hot rock rises from deep within the Earth. Rock so hot it glows like molten metal, carrying the heat of the planet's interior toward the cold ocean floor. As this liquid stone meets the icy water of the deep sea, something magical happens. The meeting of fire and ice creates a symphony of transformation. The molten rock cools instantly, forming pillow-shaped mounds of fresh stone. Steam rises in great clouds, carrying minerals dissolved from the hot rock into the surrounding water. The temperature difference between the rising magma and the deep ocean creates currents that swirl and dance through the underwater valleys. This is Earth's most productive factory. Here, new ocean floor is manufactured at a rate of inches per year. That might seem slow, but remember that this process has been continuing for billions of years. Over such vast stretches of time, those inches become thousands of miles of new sea floor. Picture a conveyor belt made of stone. At the ridge crest, new rock forms and immediately begins moving away from the crack. As more new rock emerges behind it, the older rock is pushed further and further from its birthplace. Slowly, steadily, the ocean floor spreads outward from the ridge like a scroll unrolling in both directions. This spreading creates room for more hot rock to rise. More new crust to form. The process feeds itself in an endless cycle of creation that has been reshaping Earth's surface since the first oceans formed. The new rock that emerges at these ridges is different from the rock that forms continents. It's dark and heavy, rich in iron and magnesium. This is basalt, the fundamental building block of ocean floors. It forms in characteristic patterns as it cools, sometimes in the pillow shapes created by rapid cooling in water, sometimes in tall columns that crack into geometric patterns as they shrink. As the fresh basalt moves away from the ridge, it carries with it a record of Earth's magnetic field at the time it formed. The iron minerals in the rock align themselves with the planet's magnetic poles like tiny compass needles frozen in stone. This creates stripes of magnetized rock that run parallel to the ridge crest, preserving the history of how Earth's magnetic field has changed over millions of years. The spreading ridges are also gardens of life unlike anywhere else on Earth. Around the hot springs where magma heats the ocean water, unique communities of creatures thrive in the darkness. These organisms don't depend on sunlight for energy. Instead, they feed on the chemicals dissolved in the hot water rising from Earth's interior. Giant tube worms grow in clusters around the hottest springs, their red plumes filtering nutrients from the mineral-rich water. Ghostly white crabs scuttle across the newly formed rock. Bacteria form mats of brilliant color on the warm stone surfaces. These communities exist in complete independence from the surface world, creating their own ecosystem powered by the planet's internal heat. The spreading process is not uniform across all ridges. In some places, the plates pull apart rapidly, creating wide valleys and fast-spreading sea floor. In others, the separation is slow and gentle, forming narrow rifts and thick new crust. Each ridge has its own personality, its own rate of growth, its own unique contribution to the ocean's expanding floor. Sometimes the spreading is interrupted by fractures that run perpendicular to the ridge. These transform faults allow different sections of the ridge to move at different rates, creating a zigzag pattern that accommodates the complex geometry of spreading on a spherical planet. The result is a system of ridges and valleys that looks like a vast underwater lightning bolt when viewed from above. As the new ocean floor moves away from the ridges, it begins to cool and settle. The rock contracts as it loses heat, causing the sea floor to sink gradually deeper. This is why the deepest parts of the ocean basins are found far from the spreading ridges, while the highest underwater mountains are at the ridge crests where the newest, hottest rock emerges. The cooling and sinking process creates the characteristic profile of ocean basins. shallow near the ridges where young rock still retains its heat. Deeper toward the centers where older rock has had time to cool and contract. This gentle slope from ridge to basin center channels the flow of deep ocean currents and influences the circulation of water throughout the world's seas. The spreading ridges also play a crucial role in regulating Earth's climate. The hot springs along the ridge crests add heat to the deep ocean water. They also release dissolved minerals and gases that affect the chemistry of seawater. These chemical changes influence how much carbon dioxide the oceans can absorb from the atmosphere, which in turn affects global temperatures. Over geological time, the constant creation of new ocean floor at spreading ridges balances the destruction of old ocean floor at subduction zones. The planet maintains a steady total surface area by creating new crust in some places while recycling old crust in others. It's a global system of renewal that keeps Earth's surface fresh and active. As you rest tonight, picture this hidden symphony playing out in the darkness of the deep ocean. Thousands of miles beneath the waves, hot rock rises to meet cold water in an eternal dance of creation. New stone forms with each passing moment, adding to the foundation that supports all the water of the world. This rhythm of creation and spreading, of fire meeting ice in the planet's most secret places, forms part of a larger cycle, a grand recycling system that ensures nothing on Earth is ever truly lost, but instead transformed and renewed in patterns as old as the world itself. There is something deeply comforting about knowing that nothing on Earth is ever truly lost. Every grain of sand on every beach, every crystal in every mountain, every pebble in every stream. All of them are travelers on an endless journey of transformation, participants in the planet's most beautiful dance, the great recycling dance that has been choreographed over billions of years. Your Earth is the ultimate recycler. Not just of paper and plastic and glass, but of the very stones that make up the ground beneath your feet. The rocks that seem so permanent, so unchanging, are actually on their own patient journey through cycles of creation, destruction, and rebirth that span millions of years. Picture the life story of a single grain of quartz crystal. Perhaps it begins its journey in the heart of a mountain, formed when hot magma cooled slowly deep underground. For millions of years, it rests in the darkness, part of a massive granite formation, surrounded by other crystals in a matrix of cooled stone. But mountains, no matter how tall and strong they appear, are not permanent. Rain falls on the peaks. Ice forms in the cracks. Wind carries away tiny particles day after day. Slowly, grain by grain, the mountain begins to surrender its substance to the forces of erosion. Our quartz crystal eventually breaks free from its granite home. It tumbles down mountainsides in rock slides. It travels in streams and rivers, growing smaller and more rounded with each mile of its journey. Eventually, it reaches the sea, where it settles on the ocean floor as part of a layer of sand and mud. Here, the crystal might rest for millions more years. But Earth's recycling system is patient and thorough. As more and more sediment accumulates above it, our quartz grain gets buried deeper and deeper. The weight of all that overlying rock creates pressure. The heat from Earth's interior warms the buried sediments. Under this pressure and heat, something remarkable happens. The loose sand and mud slowly transform into solid rock. The quartz crystal becomes part of a sandstone formation, cemented together with its neighbors in a new kind of stone. This process, called lithification, is like Earth's way of binding scattered pages into a book. But the recycling dance is just beginning. The ocean floor where our sandstone rests is part of a moving plate. Slowly, steadily, it drifts toward a place where it will meet another plate. When that meeting happens, our sandstone layer, along with all the fossils and minerals it contains, begins a journey into the depths. This is where the dance becomes truly extraordinary. As the ocean plate carrying our sandstone dives beneath a continental plate, it carries the rock deeper into Earth's interior than it has ever been before. The pressure increases dramatically. The temperature rises until the rock begins to change at a fundamental level. Under these extreme conditions, the sandstone transforms once again. The quartz crystals recrystallize. New minerals form. The rock becomes something entirely different, perhaps a schist or a gneiss, with bands of different minerals creating beautiful patterns like frozen lightning. This transformation, called metamorphism, is Earth's way of rewriting the story contained in stone. But even this is not the end of the journey. As the recycling plate continues its dive into the mantle, the temperature becomes so intense that the rock begins to melt. Our quartz crystal, which has already been part of a mountain, a beach, and a transformed metamorphic rock, now dissolves into liquid magma. In this molten state, the atoms that once formed our crystal mingle with atoms from countless other rocks. Materials from ancient ocean floors mix with fragments of billion-year-old continents. Elements that once sparkled in the sunlight at Earth's surface blend with materials that have been cycling through the planet's interior for eons. This magma, enriched with the recycled materials from the surface, begins to rise. It's lighter than the solid rock around it, so it moves upward through cracks and weak spots in the overlying stone. Some of it reaches the surface as volcanic eruptions, creating new land from old materials. Some of it cools underground, forming new granite bodies that will one day become new mountains. And so the cycle begins again. The atoms that were once our quartz crystal might become part of a volcanic island. They might cool slowly underground to form new granite. They might emerge as crystals in a geode, sparkling with colors they never had before. The possibilities are endless, but the materials are the same, endlessly recycled, endlessly renewed. This great recycling dance happens on a scale that dwarfs human understanding. Entire continents participate in the dance. Ocean basins open and close like flowers blooming and wilting in time-lapse photography. Mountain ranges rise and erode away. Seas advance and retreat across the land. The dance has many partners and many rhythms. Some cycles are relatively quick, a few million years for sediments to be buried, compressed, and uplifted again. Others take hundreds of millions of years as rocks travel from the surface deep into the mantle and back again. Some materials spend so long in the planet's interior that they witness the rise and fall of entire geological eras. But perhaps the most beautiful aspect of this recycling dance is that it connects everything. The calcium in your bones might once have been part of an ancient coral reef. The iron in your blood might have formed in the core of a star and later traveled through volcanic eruptions and weathering cycles before finding its way into the food chain. The carbon atoms in your body have likely been part of countless other life forms over the eons. They might have been exhaled by dinosaurs, absorbed by ancient plants, dissolved in prehistoric oceans, and locked away in limestone formations before becoming available for new life to use. Even the water you drink participates in its own recycling dance. It evaporates from oceans, condenses in clouds, falls as rain, flows in rivers, soaks into groundwater, and eventually returns to the sea. But along the way, it might spend centuries frozen in glacier, millennia trapped in underground aquifers, or brief moments in the bodies of living creatures. This recycling system is what keeps Earth alive and dynamic. Without it, all the light elements would eventually separate from the heavy ones. The continents would become permanently separate from the ocean floors. The atmosphere would lose its connection to the solid Earth. The planet would gradually become lifeless and static. Instead, the great recycling dance ensures that materials constantly move between Earth's different reservoirs. Elements flow from the atmosphere to the oceans to the crust to the mantle and back again. This circulation brings nutrients to the surface for life to use. It regulates the planet's temperature by moving heat from the interior to the surface. It renews the chemistry of the oceans and the atmosphere. The dance also creates the incredible diversity of rocks and minerals that make Earth so geologically rich. By subjecting materials to different combinations of pressure, temperature, and chemical environments, the recycling process generates thousands of different types of crystals and rock formations, each one beautiful in its own way. As you prepare for sleep tonight, remember that you are part of this great recycling dance. The elements in your body are ancient travelers that have seen the birth and death of countless worlds within our world. They carry within them the memory of stars and supernovas, of early seas and primitive atmospheres, of the long journey that brought them to this moment in your living cells. And when you awaken tomorrow, you will still be part of the dance, participating in Earth's endless cycle of renewal, living on a planet that has never stopped moving, never stopped changing, never stopped transforming the old into something beautifully, mysteriously new. As you settle into the comfort of your bed tonight, take a moment to feel the solid ground beneath you. Feel how stable it seems. How permanent. How utterly still. But here's a beautiful secret that will change the way you think about your world forever: the ground beneath you is dancing. Right now, as you read these words, the enormous plate of Earth's crust that holds your home is moving. Sliding across the planet's surface like a vast raft on an ocean of flowing rock. You cannot feel this movement because it happens so slowly. Slower than the growth of your fingernails. Slower than the movement of our hands on a clock. But it never stops. This is what it means to live on a dancing planet. Every step you take, every breath you draw, every dream you dream happens on ground that is in constant, gentle motion. You are a passenger on a journey that began billions of years ago and will continue long after the last star burns out in the distant future. The dance is so slow that entire human civilizations rise and fall while the plates move only a few inches. The ancient pyramids of Egypt have traveled less than the length of a football field since they were built. The Rocky Mountains have shifted westward by barely a mile since the first humans walked beneath their peaks. Yet this imperceptible movement shapes everything about your world. The continents you know, the oceans you love, the mountains that inspire you, the valleys that shelter you, all of them exist because of this patient, persistent dance of stone. Right now, North America is sliding slowly away from Europe. The Atlantic Ocean grows wider by about an inch each year as new sea floor spreads along the mid-ocean ridge between them. If you could live for millions of years, you would see the ocean expand like a flower slowly opening its petals. Meanwhile, the Pacific Ocean is shrinking. The ring of fire that circles its edges marks the places where old ocean floor dives back into Earth's interior. The Pacific Plate carries the Hawaiian Islands northwest at about the same rate your hair grows, moving them toward their eventual destiny in the deep ocean trenches near Alaska. Australia drifts north toward Asia so slowly that koalas and kangaroos will never notice the journey. But over geological time, the continent will travel thousands of miles, eventually colliding with Southeast Asia to create new mountain ranges in a future Earth that we can barely imagine. Africa pushes slowly against Europe, continuing the ancient collision that built the Alps and continues to raise them higher. The Mediterranean Sea, caught between these moving landmasses, is gradually shrinking. In the distant future, it may disappear entirely as Africa and Europe complete their embrace. India, which was once an island continent drifting alone across an ancient ocean, continues its northward push into Asia. This collision, which began tens of millions of years ago, keeps lifting the Himalaya mountains higher. Mount Everest grows taller by a few millimeters each year, pushed skyward by the patient pressure of moving continents. Even California participates in the dance. The San Andreas Fault marks the boundary where the Pacific Plate slides northwest past the North American Plate. Los Angeles, riding on the Pacific Plate, moves slowly toward San Francisco at about 2 inches per year. In 10 million years, they might be neighbors. But the dance is not just about the big movements of entire continents. It's also about the countless small adjustments that happen as the plates interact with each other. Every earthquake is a moment when the dancing partners adjust their steps. Every volcanic eruption is a place where the deep music of the dance reaches the surface. The dance creates the landscapes that define your daily life. The gentle hills where you might walk. The rivers that provide your water. The valleys that cradle your cities. All of them owe their existence to the patient interactions of moving plates over millions of years. Mountain ranges rise along the edges where plates collide, then slowly erode as wind and water carry their substance to the sea. The eroded materials become new sediments on ocean floors, eventually to be recycled into new mountains in new places. The dance is also a cycle of creation, destruction, and renewal that keeps Earth's surface forever young. The dance affects the climate that surrounds you. When continents move toward the poles, they can trigger ice ages as snow accumulates on the cold landmasses. When they cluster near the equator, global temperatures can rise as ocean currents change their patterns. The positions of the continents help determine whether your world is warm or cold, wet or dry. The dance even influences the evolution of life. When continents separate, the animals and plants on each piece evolve in isolation, creating new species. When continents collide, different forms of life meet and compete, driving evolution in new directions. The patterns of life on Earth reflect the ancient choreography of moving landmasses. Living on a dancing planet means that your address is constantly changing, even though you never move. The coordinates of your home shift slightly each year as your continent drifts to a new position. You are traveling through space not just on Earth's orbit around the Sun, but also on your continent's journey across the planet's surface. The dance connects you to deep time in the most intimate way. The rocks beneath your feet carry the memory of ancient collisions and separations. The minerals in the soil of your garden have traveled across oceans and through mountain-building cycles. The very atoms in your body have participated in this dance for billions of years. Sometimes the dance makes itself known through earthquakes that remind us of the immense forces at work beneath our feet. But most of the time, it remains hidden, a secret movement that only reveals itself to those who know how to read the language of stone and time. The dance is also a promise of change. The world map you learned in school will look different in the future. New oceans will open. Old ones will close. New mountain ranges will rise. Today's coastlines will become tomorrow's interior landscapes. The dance ensures that Earth will never become a static, unchanging world. As you lie in your bed tonight, surrounded by the familiar sounds of your home, remember that you are riding on a fragment of ancient sea floor that was lifted up and transformed into dry land. You are resting on recycled stardust that has been shaped by billions of years of patient geological processes. The walls around you are made of materials that have danced through countless cycles of creation and renewal. The water you drink has fallen as rain on mountains that no longer exist and flowed in rivers that carved valleys now buried beneath newer landscapes. You are part of the dance simply by being here. Your body is built from elements that came from the dancing Earth. Your life is sustained by processes that depend on the planet's geological activity. You are not separate from the dance, you are one of its most beautiful expressions. As sleep draws near and your breathing slows to match the rhythm of your resting heart, feel yourself settling into harmony with the deeper rhythms that surround you. The dance that moves continents. The cycles that renew the world. The patient, persistent forces that have been shaping your home since Earth was young, and will continue long after you have become part of the dance in ways you cannot yet imagine.